Hey guys, welcome back to Genius Learning. Alright, in this video I want to show how to calculate the magnetic field using Ampere's law. And in this example we have a coaxial cable and we have this current density given. J is equal to A, which is some constant, S Z hat. Alright, so I've drawn this same cylinder here. And so this is the face of the cylinder. And before I start, I want to go over some coordinates for the cylinder and the coordinates that I'll be using. And so usually we have that this is a length of R. Okay, phi sweeps from X all around the XY plane. And we still have Z as the length or the height of the solenoid. Okay, so for this problem, we want to find the magnetic field for S less than A. So that's anywhere inside this pink region right here. And so this length right here represents S, which is any length less than R. Okay, since we have labeled here A, inside of here is going to be S. Okay, so that's where the S comes from. And then here we're still going to have our height, and our phi is in the XY plane. Okay, so let's take a look. Inside of A, which is the radius of this solenoid, we're gonna put an Amperian loop, just like that. And that Amperian loop has a length of S. Whoa. All right, has a length of S. So let's write our formula for Amperian loop for a magnetic field. Okay, so we have the magnetic field dotted with the differential length of the Amperian loop, and the differential length is just going to be the circle right here of outline, okay, which is the circumference. So that's the differential length. And so we're going to do the integral from 0 to 2 pi of S d phi, and the B we'll take outside. Okay, S d phi is an arc length, so it's the distance out, S, and then d phi sweeps all the way around, okay, all the way around here. So it's coming out like this, and then the phi all the way around 0 to 2 pi. So that's how we get this part. And then mu naught is the permittivity of free space times I enclosed, which is the charge enclosed. So here we're going to get B is equal to 2 pi S, okay, mu naught I enclosed. And then if we divide by this and leave the B, then we're going to get mu naught I over 2 pi S. And all of this is in the phi hat direction. Okay, and we know that because of the right hand rule. So if in the Z direction is where our current is going, right, that's what we're given, then putting my thumb in the direction of the current and wrapping my hand around the solenoid, you could see that it's the same thing as doing this. And when I wrap my hand around the solenoid, right, it's in the phi hat direction. So using the right hand rule, we know that this is correct. Okay, so now this current here represents the current that flows from the center all the way to the outside. All right, and we're only interested in a piece that is less than that. And so we need to find this proportionality constant. Okay, so we have to find I, and we have to find it from 0 to A. All right, and this is also the formula for I enclosed. Okay, N hat dA. So this is the first step we need to do. We need to find this proportionality constant because this represents the current density of the entire coaxial cable, and we're looking for a region inside of it. And so we can't use the entire thing. We want to use a different increment as we go inside. Okay, so let's take a look at what we get. We got I is going to equal two integrals, right? We're going to be looking for 0 to a, and j is given as as z hat, okay, dotted with the n hat. So the n hat of the Amperian loop, right? This is our Amperian loop, and the n hat is facing upward, and so that's the normal of the Amperian loop, which is in the z hat. And so now z hat dotted with z hat is going to give us 1, and the differential area is going to be s ds d phi. Okay, it's going to be s ds because we have a length. So I'm going to show it here. We have a length out, okay, and then since we want to check the integral from 0 to a, right, we got to add another distance here, ds, and then we have d phi, which goes all the way around. Okay, so a length out of s, and then another length, differential length of s, because we want all the way out to the outside, and then d phi. So now these two are equal to 1, and the d phi is from 0 to 2 pi. Okay, so let's evaluate these integrals. So the outside integral is going to be 2 pi. The a can come out, and we're left with the integral from 0 to a of s squared ds. So let's evaluate this integral. We got s squared, so the integral is going to be s to the third over 3, and that's going to be evaluated from 0 to a. All right, and writing everything out, let's see what we get. Here, if we evaluate this integral, we're going to have a to the third over 3. All right, so now let's rearrange this and solve for a. So we got a is equal to 3i divided by 2 pi a to the third. Right, now this is our proportionality constant, and so we need that in order to evaluate the I enclosed anywhere in this region. Okay, so proportionality constant. All right, now let's find the I enclosed that we originally needed. So this is our formula, all right, to find I enclosed. And this time, instead of going from 0 to a, since we have our proportionality constant, now we can go from 0 to s, which is what we needed originally. Okay, so we need to go something less than a. And so we got I enclosed is going to equal two integrals. This one is from 0 to s. J, we know, is as z hat. Normal to the Amperian loop is z hat. And then we have s ds d phi, just like this integral here. Okay, so z hat dotted with z hat is equal to 1. And we know what a is equal to. Okay, so we have 3i 2 pi a to the third. And now we bring down everything else, which is s squared ds, and we'll evaluate the outside integral, which is 2 pi. Okay, and we're still left with one integral that we have to evaluate. So s squared is going to be s to the third over 3, evaluated from 0 to s. And all the constants out here, we can cancel out 2 pi, leaving us with I enclosed is going to equal 3i over a to the third. Okay, evaluating this integral here, it's just going to be s, because that's the limit of integration, so we can leave that, and we can cancel out these 3's. So finding the I enclosed, we get I s to the third over a to the third. Okay, so this right here is what we needed in order to evaluate the magnetic field of the inside region of this solenoid. Okay, so now we plug it in. We needed this, and we calculated it here, so let's write B. The magnetic field in this region is equal to mu naught, which is the permittivity of free space. I'll write down everything down here first, 2 pi s, and then I enclosed is going to be I s to the third over a to the third. Okay, and we know that that's in the phi hat. And so we can cancel one of these s's out, and we're left with, finally, mu naught I s squared over 2 pi a to the third. Okay, and this magnetic field here is the magnetic field in the region where s is less than a. So anywhere along this area here, as long as it's less than a. Okay.